So yeah, we shall move on to the panel portion. Hopefully people can start posting some questions in the Rocket chat, and we'll use those mostly to drive this discussion. The panelists will be the contributed talks that we have seen so far today, including the 2 opinion contributed talks, which also means if any of the authors of the contributed talks are watching right now and have not yet joined the Zoom, now would be an excellent time to jump in, and my lovely co-organizers will add you in as you come. Yeah, so let's get started. There have been a lot of questions, a lot of discussion in the contributed talks as a whole about this idea of generalization. And obviously generalization is incredibly important to any sort of machine learning field, including reinforcement learning. But it also seems a little challenging to define in reinforcement learning. We've seen some ideas today of generalizing to test environments. We learn on some environment, we make some small changes to the environment, and then we move on to test on these environments that have some small changes. And I'm curious to know, what are your impressions on these definitions of generalization? How should we be measuring generalization? What sort of metrics already exist? I'll go ahead and pass that question off to Sergey as the rest of our contributed speakers are coming in.
Sure, yeah. So, I mean, to some degree, it's situational and domain dependent. But I do think that, you know, it would be much more interesting if we kind of got in the regular habit of having evaluation protocols that do measure generalization. The simplest way to do it, honestly, is you don't even need to change abstractions or representations or anything about the setup. You could just have a setting with diverse initial states. And the fact that we don't have that is, you know, it's just like an artifact of particular benchmark MDPs that we picked. So the simplest thing, just make sure that your evaluation has you know, the MDP has varied initial states. But there's fancier things you could do. You could have like held out conditions, stuff like that, and that all fits into the standard framework.
By the way, I forgot to mention, if any other panelist wants to just jump in at any point, do feel free to. I think, Wilka, I saw you raise your hand.
Yeah, I have I think like probably well thought of thing, which is like, I'm really inspired by looking at like animals like ravens. And I think one thing that we can do more of, and I think we're heading in that direction, is maybe having some like standard rewarding thing in the environment, similar to how ravens have food. But then generalization is tested in a completely different environment from what agents are accustomed to. And it requires, like, so, you know, ravens, for example, have never seen tubes with water. They have to put a block in order to get the food to come out. Like, if you guys have seen videos of ravens, I think environments that are dramatically different and really just test kind of like general primitive skills are probably, but you have to have some common space. So like maybe some common space of like rewarding objects that test, that, you know, showcase the agent's ability to generalize to a completely different setting.
Yeah, I think Pete has his hand raised. Go ahead.
Thanks. Yeah, to jump off on a few of the points here. One, Wilka, I like the ravens, and there's many other animals of nature, like dogs, for example, are just so good at learning from, you know, just treats every once in a while, maybe clickers or you know, so many different ways of training dogs. Yeah, I think to me that sort of pushes RL in the direction of things that are more achievable in the real world. You know, sort of sparse rewards are much more doable in the real world rather than dense rewards. I'm also very interested in, you know, types of feedback that we can give in the real world that might not just be food or not food, but also, you know, language has such a rich diversity of, you know, just unconstrained natural language, rich diversity of things that can be suggested to improve on in, you know, more specific ways rather than just this was good or this wasn't good. I also wanted to plus one Sergey's point that many standard RL environments have very small initial state sampling distributions. And in my experience, even ones that, you know, the environment seems very rich, but if you actually look at the code that does the initialization, there's maybe a little bit of randomization, but it's maybe only over a few of the degrees of freedom. And I think another, I think going forward for the field specific useful test, for designing new environments is just how well does a nearest neighbors baseline do? So given some like demonstration data, if you just do nearest neighbor lookup of the closest observation in the data set from the demonstrator and just use exactly the action, I think that's a good way of testing not only the initial state distribution, but essentially like how well open loop policies can do in the environments. And then one more thing on the topic of generalization, we have there's been a bunch of debate on my research team recently around, I think it's really interesting for folks in sort of practically in RL and robots world, do we care about the test set actually being different than the train set? So is our notion of generalization that the test set has to be somehow distinct from the train set? Or do we really just care that we do well on a test set? And what it sort of drives at is like, would it be satisfying, would it be considered generalization if we just trained on everything ever? And then the test set would, of course, be a subset. So yeah, there's this little subtle distinction there of like, when we're thinking about generalization, if we are increasing our training data size and it is now subsuming our test data just because there's nowhere else for test data to live, do we still consider that generalization?
But one thing I might also add to this actually is that, I think that there's just this tendency that when we work on problems that are narrow, I think the question of how we deal with generalization becomes really complicated and seemingly very difficult. But when we work on problems that are broad, somehow actually things become simple. So this is a case where more realistic things might actually be easier. Like, if you were like doing supervised learning, you train on MNIST and you want to generalize to letters instead of numbers. Okay, that's just impossible. Like, you just can't do it. But if you train on like ImageNet, now generalizing to a new kind of a new breed of dog actually seems pretty reasonable. So this is kind of one of those cases where the harder problem might actually make things easier.
Definitely, very much agreed, Sergey.
That brings us to one of the audience questions that I think quite matches this discussion, which is what sort of features or properties of these environments or problems that we are looking at should we start encouraging? What are we missing in our current set of benchmarks and test beds, Atari or GridWorld or Mountain Core, or anything in between that we would be able to use or leverage in order to measure these generalizations? I see Danujar is here. Maybe you want to start us off with this.
Hey, sure. Well, I think procedural generation is pretty important. Otherwise, in Atari, you can just see the same frame multiple times and you can just attend to weird details like the pixel in the corner here, and then that tells you always to go to the left or to the right. So I think that's a good start. I think that's actually, to me, the more interesting or more important form of generalization. Then to generalize to visual, like different textures and so on. Of course, that's also useful when you're generalizing, when you're trying to generalize to a different visual domain, like sim to real. But yeah, I think just a lot of procedural generation in the way the environment is set up is pretty important. And then, of course, the more agents there are in the environment, it doesn't have to be like a actual multi-agent setup, but you can just have one agent and then there can be some like creatures or enemies or friends, AI friends, or just scripted things. And the more complex their behavior is, that also adds a lot to the potential situations that the agent may end up in. And I think if the environment is really challenging, then generalization translates pretty directly to sample efficiency as well. So then you can measure, then maybe you don't need a specific holdout set, but if you're getting closer to actually solving the environment, then it becomes more important to have an explicit holdout set for evaluation.
If no one else wants to go, I can chime in on this. I really like the bit in Fabian's question about the analogies, how to learn to make analogies. And I was thinking about that a little bit after I saw the question. And so something that occurs to me here is that, well, the diversity of situations that we as humans encounter is probably one of the things that drives us to need to make analogies. Like, if you have such a variety of things, you need to somehow organize them into a smaller set of classes. And where that leads us to next is that, well, if we want to study this in a reinforcement learning context, we can ask, how do you structure a research agenda in reinforcement learning around open world problems? I mean, there is kind of the one that Peter was getting at, well, okay, just like buy a robot and like actually do learning in the real world, but that's kind of hard. So you could think of other ways to do it. You could, for example, think of doing reinforcement learning in closed world environments, but with open world prior knowledge. You know, one thing that I sometimes suggest to people half as a joke is, can you learn to play Montezuma's Revenge by watching Indiana Jones? Or for that matter, learn to survive on a deserted island by reading Robinson Crusoe. But this is only half of a joke. Like you could imagine actually structuring some problems where you have prior knowledge from open world settings and then an evaluation domain where you have to apply that knowledge. And I think that can start getting at part of this, like that will drive you to have to make analogies to adapt efficiently. So that could be something to consider.
Another question in the chat. So there's this general theme about reward specification. That reward specification is difficult. And one of the strategies that we have talked about more generally through a lot of these contributed talks is this idea of using prior data or past data, offline data to try to infer rewards or to learn value functions or policies even offline. How does this extend to the difficult real world problems, for instance, the desert island? To get our agents that truly generalize and adapt, are we relying too much on humans in the loop? I'm going to pick on Wilka. I don't know if you want to try to take a stab at starting to answer this. I know this is fairly related to your opinion talk. You can also feel free to unmute and say no, and I'll pick someone else.
Yeah, and I was in the middle of thinking about it. Reward specification relying on humans in the loop, right? Yeah, that's a good question. I mean, yeah, I mean, part of what I think is challenging is, yeah, like the environments we use and the small changes we make to them, and then that we do rely on humans for defining reward. I keep going, like for all the questions I've heard so far, including the last one, which I didn't give an answer to, for me, it really feels like what we need is some setting, like a yearly competition or something, where the environment is just so dramatically different from what everyone is working on over the year. But whatever agent you've built, it has to do intelligent things in that environment. And I think that we still need humans in the loop there to but maybe it can be crowdsourced, like the whole world or game designers are thinking about cool things that everyone would enjoy, but it's not tailored to like specific kinds of generalization. We know that if an agent can generalize in this way to like this completely different environment, it's probably an agent that's like relatively general, like in the similar way that, any one of us could probably see this random environment that I'm imagining and be able to quickly learn it because we have a good set of primitive skills from our experiences in the world. Not sure if that's, yeah, anyways, what are my thoughts?
All right, I'm going to change the topic of conversation just a little bit, and that we've hit maybe a little bit of a lull. So there've been several suggestions on environments, benchmarks, metrics, perhaps that we need to start focusing on in order to obtain more general agents. I'm curious now about the algorithm design component. So a lot of the talks today have talked about this idea of tasks and temporal abstraction. We've talked a bit about using prior knowledge and inductive biases, even structuring our representation in certain ways in order to achieve some of these generalization properties. So what sort of algorithmic developments should we start targeting, and what sort of next steps do you think we should see in our algorithm development? And I'm going to pick on Averil to get us started here. You can feel free to take a minute to think about it if you'd like.
Yeah, thanks a lot for asking the question. So one of the things that and this is probably just my bias about this a little bit, but one of the things I personally think is lacking from current algorithms is the ability to be able to use them in practice. I mean, right now, for instance, I don't even know if I just drastically scaled up a particular already existing RL method, would it perform well or not on a new problem I care about, on the best possible environment we can design, and so on. And part of the reason I think is we kind of don't understand, first of all, how do these algorithms work? Secondly, how do I debug an algorithm if it breaks, or where is it breaking, or so on? Third, I don't know, like kind of how do I use big networks? How do I scale up things with deep RL methods? And so I personally think that kind of while there's this one exciting avenue of devising algorithms for new settings and making them more robust and generalizable and so on, even kind of going back to the fundamental questions, the most simple environments we have, even grid world type environments, and trying to understand where and why are current algorithms breaking and improving them in that way is kind of a reasonable exercise, I think. Kind of some of the, like my contributor talk was also based on something like that. It was basically simple Atari games or simple grid worlds and trying to see where TD learning algorithms break. So perhaps something of that sort, in my kind of very biased view, could be a reasonable starting point for algorithm design. Yeah, that's, I guess, mainly what the first thought here is. Yeah.
I see Pete has unmuted. I don't know if you had something you wanted to add.
Sure. Yeah, I would plus one what Avril said, and I think it's a great answer. It's also kind of funny that, like, the answer to, like, oh, what should we do for algorithms? And, a very reasonable answer is like, maybe we don't need any more algorithms. We just need to sort of, make our existing algorithms easier to use and better tested. And I think that, yeah, to Avril's point, the sort of the existing MDPs that we have are useful, but then, kind of going back to the previous question, like, I do think to a certain extent, if we do a whole round of just evaluating all existing algorithms, but it's somewhat overfit to the current set of environments, then, we, of course, sort of might need to kind of redo all that analysis on the environments that we were talking about earlier that might have more aspects that we think are increasingly relevant to more real world problems. And I do think too, in terms of, Sergey and others were mentioning the idea before of having, just experience that comes from completely different places, sort of like open world experience, or, I like to think of, experience or data that is just completely free, like, like literally watching all of YouTube, or just downloading the variety of, pre-trained models or huge data sets that we can pre-train common sense on, and then quickly adapt to new environments. I think that would, be a holy grail of sorts. And to plus one what Wilka said, I think it's hard to codify it specifically in test environments, but the ability that humans have to just sit down and quickly learn a new video game and figure out what to do, I think is certainly one type of inspiring way to think about how we could increasingly design better test environments. But also, I would also say one more thing, which is that, to the question of algorithm design, I think there's plenty of opportunities, but I think I would plus one overall that evaluation to me seems like maybe the area that the field needs more of at the moment.
I can give some thoughts on this too. This is maybe a little related to what Avril said, and maybe part of the takeaway from his talk too is that this is it's a little in the weeds, but when we do deep RL research, I think we have a tendency to either do RL research or deep learning research. There's actually surprisingly little deep plus RL. And I don't want to make too sweeping of a statement, because there's definitely work on functional approximation in the RL setting, like it's definitely a thing, but surprisingly little of it. And I think that one really interesting takeaway from the work that Avril presented is to consider that, maybe deep RL is not just RL stapled together with deep nets. Maybe there's actually like really complicated questions that start to arise, and maybe things that work in supervised deep learning do not work in deep RL for a good reason. And we really need to consider those two things together. So, for those of you in the audience that are looking for like meaty, juicy technical things to tackle, like I think there's actually a lot of open problems there. And, hopefully Avril made a case for that in his talk too to you.
To add on to that, I think there's also a lot of maybe not quite as difficult, but still important questions around I think deep RL has becoming more and more stable and moving closer to supervised learning in terms of just, people like you can benefit from all these network architectures, for example, that are successful in vision, which people are just starting to figure out how to use them in the RL world, but they lead to huge improvements. And I think there's a lot that we can kind of import into the field of RL now that things are more stable and a bit more figured out. And I think we'll see some big improvements just by making models better or bigger and like using more modern network architectures and training schemes and so on. And I think the other exciting aspect of that is, of course, that we're then unifying RL a bit more with the other deep learning fields, and we can transfer ideas more quickly between those boundaries.
Yeah, I want to plus one this and also Sergey's comment. Yeah, I think a deeper integration of deep learning and reinforced learning is really an exciting future that I think that we're beginning to go towards. And I think it'd be really cool if we had, like unified architecture algorithms. But I think the key question is like, what are objective functions that don't just, maximize, that don't just learn a policy on top of a deep RL architecture. I didn't have a lot of time to talk about it, but I really think generalized value functions play a really key role here, and not just like having policies be an integral part of the architectures we learn, along with predictions about the world. But I think, yeah, there's a lot of space to think about that. Yeah.
Gathering a handful of questions from the audience and trying to smush them into maybe one coherent question. We'll see how that works. There's been a lot of discussion on using this prior knowledge and this inductive biases. And part of generalization, or part of the goal of doing that, is in order to generalize to environments that are different perhaps at this training time versus test time, but also to generalize to build agents that can generalize to environments that are just constantly changing. So for instance, Fabian asked, what happens if the laws of physics are constantly changing within our environment, and having agents that can generalize to that. And so we need, say, a new set of benchmarks or environments that allow us to test sort of this form of generalization. Kind of on that theme is the idea of this distribution shift, our change in data that we see coming into our agent, and the questions that we are expecting it to answer. And so are there sets of environments or benchmarks that we should be looking at for this form of generalization? And also, what sort of algorithms should we use to tackle that particular problem? And I'm going to start with Ashvin, if you want to get us started here.
Yeah. So one like angle on this that I've been personally very interested in, which is kind of it's only possible in RL, is that you don't need to be pursuing like zero-shot generalization in the same way that you do in other forms of deep learning, because there's often the opportunity to like generalize as much as you can offline, and then be able to interact, collect more data, and so on. And I think that's pretty important and underexplored. That we can collect new data, as long as there's like a prerequisite of the existing algorithms working well enough. Like you need good offline RL algorithms. You need ways to like provide supervision in the new environment. But I think like long term, we kind of have to move towards this, because like the amount of like data diversity that we need to handle in RL is like something like the product of like ImageNet times like actions and things like that. So I think the only way to be able to handle that is through like active interaction.
Sergey, I think I saw you react when I asked this. Did you have something you wanted to add as well? I think there's a chance Sergey is frozen. I also saw Pete react. Pete, did you have something?
Yeah, I could say something. Sorry, I didn't realize you called on me.
No way.
I was just thinking. I was on a panel yesterday for a workshop on distributional shift, not on RL, where more or less the same question was asked from the other side. But I think Ashton's answer is actually getting at a really important point, which is maybe more relevant to the folks working on distributional shift rather than the folks working on reinforcement learning, which is that the RL setting actually provides a really excellent toolkit for dealing with this. So if you're working on distributional shift from the supervised learning perspective, you're like, oh man, like, something's going to change. Like suddenly the birds will be cows and the cows will be birds. And how the heck do I label my images? But if you're doing reinforcement learning, like, well, I've got my reward signal. So given enough time, I'll still adapt. It's just a matter of adapting quickly enough that nothing really bad happens. So I think that really is kind of a match made in heaven. Like if you imagine your autonomous car drives into a new city where things are a little different, maybe there's a big construction site. You could imagine approaching it from a perspective of reinforcement learning, which presents big reinforcement learning challenges. You have to be quick and you have to be safe and so on. But it also presents an excellent toolkit for dealing with distributional shift challenges. So I think that's really something that we should be studying a lot more from both perspectives.
I'm not sure if you had something you wanted to add on to that as well, Pete.
Yeah, I was going to. Sergey kind of nicely covered in the real world, at least for robotics or many other applications as well. The safety part is I think a tricky one, and as Sergey mentioned, like I think a lot of applications, it's always very practical and realistic to assume that you could have at least a little bit of online new interaction in the new environment. You just can't destroy it or yourself. And I think ideally, although I wouldn't really necessarily want to hand code these behaviors in, having some type of recognition or having an agent which from which emerges the ability to kind of recognize, hey, I don't really know what's going on. I'm going to spend some time figuring out, maybe it's a completely new embodiment, for example, too. Another thing that hasn't come up yet, but a lot of what we do in RL or robotics research is tied to a certain set of observation action mapping, and ideally agents that could just sit down with any observation action mapping and figure out what to do, but maybe spend a little bit of time safely figuring out how the joysticks map to what happens. That would be I think a great thing to go after.
I think we have about 2 minutes left for the panel. So I will close with a very open-ended question from anonymous attendee, which is, reinforcement learning is all you need for real-world problems, right? And why? I don't want to pick on anyone specific for this question, so I'll let you sit for a second and see if someone volunteers.
Well, reinforcement learning is definitely all you need for any problem, because it is literally the problem of rational decision making. Like any agent that is doing something intelligent, like rational decision making is virtually the definition of that. I'm not sure that's a useful perspective, to be honest, though, because it's like kind of the usual thing is you can reduce something to a more basic problem. That doesn't mean that it's always the best way to solve it, right? So you could solve supervised classification with RL. That doesn't mean it's a good idea, though. So we got to be a little careful with that particular chestnut.
Yeah, but I would plus one what Sergey said, and I think also sometimes the assumptions we make about oh, we have this MDP sort of bake in things that just the definitions of what the MDPs are, for example, might not sort of fully capture all aspects that we might want for real world agents. One, for example, being, I think in practice, a lot of times it's all we need, but just sort of imagining the world as discrete MDPs. The real world doesn't, for certain applications, doesn't stop while you're sitting and thinking. So But I do think that certainly, I think you can make the argument that almost anything can be either, depending on your view, nicely fit under the RL definition or shoehorned under the RL definition. But there's certainly a lot of value in the approach.
You still have to come up with the reward function in the first place if you want to solve an actual problem. So that's often a pretty big challenge. And you could say that's also studied within the community of RL, but maybe not really the problem setting of RL itself. And then you have to do build a lot of infrastructure and in the physical world, but also just in the code. So I think there's a lot more around just like the core RL algorithm. And then, like Martha said in the chat also, RL is just a problem setting, so it still doesn't tell us what algorithm we actually need to use.
It's like saying $1 million is all you need. You still have to get the $1 million somehow.